All right, welcome to our concept presentation from HORYZN, from the mission pulse, our project mission pulse. As you know, we started our student initiative at the end of 2019, and Mission Pulse is our second project. HORYZN has 5 sub-teams: design loop, business and certification, CAD, structure, and avionics and flight testing. Now, today, we want to show you the results of our design process. And please welcome on the stage. And in the very beginning, I want to say a big thank you for this amazing work to the Design Loop SAC team. And now, please welcome on the stage Philipp Ziegler and Balázs Türkimaz. Thank you very much.
Thank you, Balázs, for the introduction. I very welcome you also from my side. I'm Philipp. I'm the current sub-team lead of HORYZN Design Loop. And together with Balázs, we will present you today the results of our design process for the project Mission Pulse and the drone, the first prototype, what's name is Frankenstein 1. To give you a short overview what we present today, so I will start with the mission profile, continue with the requirements and the conceptual design process, and Balázs afterwards will continue with the preliminary design and the results out of the parametric study. In the end, we are looking forward to question all your answers and would like to have a nice discussion with you. So starting with the project target and the mission profile. So in Germany, the average time period for an ambulance to arrive at an emergency location after the emergency call income is approximately 9 to 11 minutes, depending on where you live. So we consider suburban areas and rural areas. In case of a heart attack or a cardiac arrest, this time span often leads to a low survival chance. The target of HORYZN Mission Pulse is to provide and develop and demonstrating eVTOL that can deliver a defibrillator to an emergency location in less than 5 minutes. So with this short undercut in the time span, we can increase the survival chance in case of a cardiac arrest. How does the mission look like from the technical side? So in the beginning, we have the vertical takeoff and a rise to about 200 meters, where we transition into horizontal flight and cruise to the target location. If we arrive there, we transition back into an hover flight, descend to a height of about 50 meters, and a pilot is determined the drop-off location via a video stream. If the location is determined, the UAV let down the defibrillator via a rope mechanism, and the defibrillator is picked up by a bystanding person. If the defibrillator is on the ground, the drone hovers and climb again back to 200 meters, transition into cruise flight, and flies back to the starting hub. Let's come to the requirements. So the requirements for the mission were derived from certification side, the mission profile, our use case, and also from our flight testing team. To operate the drone, we need a SORA certification. SORA stands for Specific Operations Risk Assessment, and it's mandatory for operating UAVs. Our biggest requirement is that there's no single point of failure that leads to a catastrophic event. This is on system and propulsion basis. So I show you here the a summary of our most important requirements. So out of the SORA certification, the cruise speed is limited to 35 meters a second. And as we want to get as fast as possible to the emergency location, we use this high cruise speed as our cruise speed for the mission. From the flight testing team, we received the requirement of a stall speed about 20 meters a second. It's due to the limit area of the flight testing field, and therefore they have enough time and area for conducting all the different flight maneuvers. From our mission side, we have the requirement that we drop off the defibrillator at latest 5 minutes, 300 seconds after the takeoff. From certification side, the drone must have a span below 3 meters, and we consider a payload of approximately 3 kilograms. This includes the parachute, the AED, an AED box, and also some warning and attention systems. And also from certification side, our takeoff weight must be below 25 kilograms. So how do we get from all these requirements and the mission profile to our conceptual design? First of all, our team members from Design Loop received the requirements we summed up that the eVTOL must fulfill. And then we did some mind mapping and sketched up different concepts and discussed them and rate them. We had concepts starting with helicopter, multicopter, fixed wing configurations, and also tilt wing configurations. We considered different designs of the fuselage and the main wing and tail wing, and also different configurations of propulsion units. Two concepts were then examined further in detail using an in-house tool that we have numerical values to compare our configurations. And the final concept was then selected by using this data. So here you see two of our concepts we considered further. On the left side, we have a configuration with 8 single hover propulsion units. On the right side, we have coaxial propulsion units. So for the redundancy, because we hover and fly over populated area, we must have more than 4 hover propulsion units, and therefore we selected 2 different configurations with 8 units. We also considered what distance is needed between the rotors, and we calculated that it's beneficial to have the efficiency loss in an coaxial configuration, but have them closer together, the rotors, and have like a better inertia, and it's also beneficial for the mass. On the left side, you see also that we have wingtip rotors for the propulsion, and that's beneficial because we don't need any rudder for the stabilization and maneuver in yaw directions. And that's how we put together our final configuration. Which has like the wingtip motors for cruise flight and the hover propulsion units in coaxial for in all. The defibrillator is implemented into the fuselage and is mounted in the center of gravity. That's because in the middle of the mission, we drop the payload, and therefore we don't want to have a change in the center of gravity. We also consider that we can land on our vertical stabilizers, so on the tail, and therefore have less drag because we do not need any landing gear. Yeah, this is the final result of the conceptual design, and I would like to hand on to Balas to present you the preliminary design phase.
So thank you, Philip, for bringing us this far, and thank you, Balázs, for the introduction. So also from my side, welcome everybody. My name is Balázs Türkümaz, and I was the design loop lead responsible for the preliminary design and conceptual design of Frankenstein 1, which is the drone we are building currently. And currently I'm serving as an aircraft design advisor, also still in HORYZN. So let's kick it off with the preliminary design. I want to talk about the methodology that we followed for a short period. So we already had an in-house preliminary design tool for the Silencio project, which we did last year. We used state-of-the-art software when we created this design tool. For example, we used CPEX from DLR. We used the remote component environment as a toolchain manager, and we wrote our design code in mostly MATLAB, but also some portions of it in Python. We refined this tool and we use it again for Frankenstein 1 with added functionality, which we will come to later in the presentation. And after we had confidence in the results through the changes, we conducted parametric studies to determine an optimized variant for our mission. Now I would like to introduce you quickly to our design loop logic with a flowchart. So let's start with our inputs. We have our high-level geometry, for example, parameters like aspect ratio, the wing loading, and the wing and empennage geometry. And we also have our maximum takeoff mass as an input. And we have our mission segments like start and end values for velocities, for altitudes, for load factors, and so on. And after we input these values into our loop, the first module to be called is the flight state module, which transforms these inputs that we gave about the mission. For example, we can say the cruise phase is 35 meters per second at an altitude of 200 meters for, I don't know, 3 minutes or something. And this interpolates the flight state module computes mission points, which are dedicated calculation points for our loop. And we get the flight states out of that. Next, we call the geometry module, with which we can create our lifting surfaces, so to say, using the maximum takeoff mass and also the high-level parameters that I mentioned earlier. And after we know our lifting surface geometries, we can calculate the aerodynamics of the configuration. We use a calculation tool called PAVAT from Bauhaus Luftfahrt and from the Flight System Dynamics Institute at our university. We get aerodynamic coefficients out of that, and also forces along the span of our lifting surfaces. And this tool is also based on a 3D lifting line method from Philips. So after this tool is run, as already mentioned, we get our drag puller and we get our forces, and the forces are passed on to the structure module from which we dimension the required thickness of our wings, and therefore we get our wing and empennage rates out of that. With these three inputs, you can see on the in the middle with the drag puller, the wing and empennage rates, and the flight states, we can go into the performance and propulsion module, where we can calculate our point and mission performance, as well as select our propulsion components from a database. And after we have selected the components, we know how much they weigh, and then we can add everything up and see if our maximum takeoff mass has converged. If it has not converged, we have to go back and repeat the calculation until it does. And when it does, we know how our converged configuration looks like. So let's take a deeper dive into the performance and propulsion module, which is more or less the heart of our design loop. So let's start with the inputs again. We get our drag polar, we get our flight states, and we also get our maximum takeoff mass. And with these inputs, we can calculate our thrust requirements. And after we know how much thrust we need at each mission point, we go into the propeller selection. And we use databases during this process. So we have commercial off-the-shelf components with their data, and we select the most. We select the propellers with the least energy demand for our mission. After that, we also have a database for motors, cables, ESCs. So we select the components which are required to drive these propellers. And after that is done, we have to do an iterative mission calculation, and we also have to size our battery. And after this step, we know the masses of each component. So we can calculate our propulsion mass, and we can check if it has converged. If it has not converged, we have to go back to the front and select new propellers, new motors, new batteries, and so on. And if it has not converged, and if it has converged, we know our component masses and centers of gravity. The main change we did in this module was the hover propulsion system now required coaxial propulsion, which it did not last year. So I would like to also quickly introduce you into the coaxial propeller selection logic. So we start with our thrust requirement, and we also have our database values for the torque and power coefficients alongside the RPM. What we do is we vary the ratio of required thrusts between the top and bottom propeller. So we say, for example, we go from the top propeller delivering all of the thrust to the bottom propeller delivering all of the thrust, and a defined number of points in between. So we calculate for each of these points the thrust requirement for the top and bottom propeller, which is more or less the thrust requirement divided by how much thrust we need to provide for that propeller. And then we go into the coaxial performance calculation, because the top propeller influences the bottom propeller. So we need to calculate the top propeller first, the needed power and torque for the given thrust. And after that, we can calculate the wake it generates. And after we know how the wake looks like, we can calculate the needed power and torque for the bottom propeller for a given amount of thrust. And after that, we selected as our design point the point where both torques are matched. So we find the ratio with which we have matched torques between the top propeller and the bottom propeller. And after we know that, we apply the same selection criteria, so which is we select the propeller pair with the lowest needed power over the whole mission. So now we're more or less done with the logic of how our software functions, and now we can go to parametric studies. And also in this case, I would like to introduce you quickly to the methodology we followed during these studies. So what was our goal? Our goal was to determine a variant with the lowest energy demand for the given mission, because our mission parameters are set by certification or from external requirements, let's say. So our goal was to compute a variant with the lowest energy demand so that we would have the most efficient and the smallest variant that we have to build. Is something else you should know from the graphs that you will see in a few minutes. Each point you will see on these graphs is a converged design on its own. So we changed the parameters and let the loop run, and we let it converge to a configuration, and then we analyzed what came out of it. We did parametric studies on the main wing aspect ratio and wing loading, also the main wing taper ratio, the tail aspect ratios, aspect and taper ratios, and also we did a study on the maximum propeller diameter. So that's because we wanted to check if our assumption was correct. When we selected the propeller with the lowest energy demand, that would lead to really the lowest energy demand for the whole powertrain. So I would like to now introduce you to some results from our designs. So on the left side on this graph, you can see the maximum takeoff mass, and on the bottom, so on the x-axis, you can see the aspect ratio along with 3 lines. These 3 lines represent different wing loadings in kilograms per square meter. So the blue line is 22 kilograms, the red line is 26 kilograms, and the orange line is 30 kilograms. So what you can see here is the aspect ratio does not really influence the maximum takeoff mass. And also another point, the results tend to sometimes jump up and down, and that is because we use commercial off-the-shelf components, so like concrete components that we have to select during our design process. We do not use a rubber engine sizing, so with every converged airplane, we get it's possible that we get different propulsion groups, so to say. So that's why there's a tendency that the mass tends to jump up and down, which you can see on this graph. On the y-axis, you can see the total energy in watt-hours, and on the x-axis, you can see the aspect ratio with the 3 lines from before. And we also can see here the aspect ratio doesn't really have that much of an effect on the total energy demand as well. The most difference is around 10%, which we can explain by our high cruise speed and our relatively large wing resulting from the stall speed constraint we were set by. And when we are underway with 35 meters per second during our cruise, our lift coefficient is probably so low that the induced drag doesn't really play that much of a role, so that the aspect ratio is also little less relevant, let's say. Another constraint we have to take into account is the span, which is actually self-explanatory. On the y-axis, you can see the wingspan in meters. On the x-axis, you can see the aspect ratio, and we have a hard constraint at 3 meters. Actually less if you take into account the wing to propulsion, because including the radius of the propellers, which if you take them away from the 3 meters, if you subtract them, we will need to have an even less wingspan to comply with the constraint. Sorry about that. Yeah, so let's move on. With the wing loading, you can see again on the y-axis the maximum takeoff mass in kilograms, and on the x-axis the wing loading in kilograms per square meter, and the aspect ratios are the ones with the colored lines. The blue line is aspect ratio 10, the red line is aspect ratio 12, and the orange line is aspect ratio 14. There is a tendency here, which we can see that with a higher wing loading, the mass tends to go down, but only until 25, 26 kilograms per square meter. After that, we can see that there are diminishing returns. Also, this is reflected in the total energy demand. We can see the total energy on the y-axis in watt-hours, and on the x-axis, we have the wing loading and the colored lines, the same as the last graph. And we can see here that the wing loading, like with rising wing loading, we get a lower energy demand until a certain point, and after that, it does not really bring us that much to further increase the wing loading. And another consideration we need to take is the stall velocity, which also depends on the wing loading. The stall speed you can see on the y-axis in meters per second. On the x-axis, again, the wing loading and the 3 colored lines. So we have to take into account the stall speed constraint here when we are selecting our variant. So that was it for the studies, and now I would like to introduce you to our results. You can see a 3 view on the left side. With the wing to propulsion, we come to 2.9 meters of wingspan, a little under 3 meters, which is perfectly fine. We have 14-inch cruise propellers and 30-inch hover propellers, and maximum takeoff mass of 16.9 kilos and an aspect ratio of 10. Ring loading of 26 kilos per square meter, and a hover disc loading of 9.3 kilos per square meter, where we took the areas of 4 discs instead of 8 discs. Soul speed is 20 meters per second, also in line with our requirement, and our energy total energy demand for the whole mission. So like flying to the cardiac arrest location and flying back is 473 watt-hours in total. So now I would also like to show you a quick mass breakdown. So we have different systems that we have. For example, our payload and delivery system is at 11%. Our battery is at 17%. Our avionics at 11%. So our structural mass is around 19%. Our propulsion mass is around 34%. And our parachute system is also around 5%. And we also have a reserve battery in case our main battery dies for some reason. The reserve battery kicks in and propels the aircraft into a height from which we can safely deploy our parachute, and that also has 4% of the mass. I would also like to show you the mass breakdown of the last year's prototype Silencio Gamma, and compare that to Frankenstein 1 for those who do not have who cannot really, who are not in UAV design, so that you have, so that you have something to compare our results to. Our payloads are more or less the same percentage, but the battery is significantly larger because we need to hover that much longer, and we cruise also really fast in comparison to Gamma. Gamma was cruising around 20 meters per second. Now we have to cruise with 35. The avionics are from the absolute mass more or less the same, but percentage-wise, Gamma has a much higher percentage because the total mass is much lower. The structural mass is the same thing also. And with the propulsion mass, we have a huge increase because we double the number of components for hover, and we also need that much more power in these in the hover system as well as in the cruise system, because we are at the end almost 50% heavier. And on top, we have components we did not have last time, for example, the parachute system and also the reserve battery. And that was it from our side. Thank you very much for your attention. And now we will be closing the YouTube stream. This might take a few moments, and after that, we would like to begin with the Q&A. I will let you know when it is okay to ask questions. Thank you very much.